Hello, and welcome to the Sigma 2025 talk on Memento filter, a fast, dynamic, and robust range filter. This is a work done by me, Naveed, and my advisor, Niv Dayan, at the University of Toronto in Oracle Lab. Okay, so what is a filter? A filter is a compact probabilistic data structure that represents a set of keys that we care about. So in this particular example, A, B, and C, and so on. The filter is able to answer membership queries. So you can give it a key X and ask if that key X exists in the set or not. Filters are typically stored on faster, more expensive memory, such as DRAM and SRAM, and they serve as an optimization to avoid redundant accesses to the actual data, which is often stored on slower memory, but more inexpensive memory, such as SSDs or hard drives. Now, the way they provide a performance benefit is if a key exists, they guarantee that they answer with a true positive. So they always tell you that the key exists if it actually does. So they never create any data loss. And if the key doesn't exist, they return a true negative with a high probability and a false positive with some small probability epsilon, which you can tune by giving the filter more memory. So the more memory it has, the less chances of a false positive it has as well. Okay. Now, filters are nice because, well, they give you these nice semantics. You can do queries, but you can only support, they only support point queries. So you can only give them a single key and ask if that key exists in the data or not. What about a range, though? What if we care about two keys, LNR, let's say, and we want to see if any key inside of the dataset is included in between these two keys, LNR? Now, this would be a range filter, and we would like our range filter to have the same types of guarantees as a normal filter. So we would like to have a low false positive rate and a high probability of true negatives or equivalently for empty range queries. Okay. So range filters are very useful. They have use cases in many different application domains, particularly in the case of database systems. Well, we have key value stores, and many key value stores are structured as LSM trees or B trees, or B tree, or we have LSM tree indices or B tree indices. In the case of LSM trees, our data, which are represented as key values, is stored in a hierarchical structure, each level consisting of a sorted file of key value pairs. Now, because this is a key value store, we oftentimes have to process range queries on it. One way to optimize range queries is instead of looking at every single one of the files, we can employ a small range filter for each one of the files in memory and query the range filter to see if that file contains any data that's relevant to the range query. And if it doesn't, we can skip accessing the file and save on IOs. Similarly, if we're working with a B-tree index or a B-tree database, we can have a single filter that represents the entire database. And before we do a range query on the entire database, we check the filter first. And if it tells us that the range query is empty, we can avoid accessing the hierarchical structure of a B-tree and save many IOs. So in a sense, in effect, range filters allow us to eliminate most of the IOs that occur in LSM trees and B trees, significantly improving performance. Because of this, range filters have become a very hot research topic in the past decade, starting from a paper back in 2014, a theory paper that defined the problem. And then in 2018, research came into the practical scene by designing many different range filters, starting from the influential paper SURF, which we are going to consider right now. We're going to talk briefly about SURF to illustrate the problems that persist to this day with the problems that persist to this day with all of these designs. Okay, so to do so, let's consider this data set consisting of 4 keys, each 4 bits long. Okay. In principle, what SURF does is that it stores all of these keys in a binary trie. It's not exactly what it does, but morally speaking, that's roughly what it does. It constructs a binary trie. And then what it does is it truncates this trie at a level such that any path you take from the such that the try is still able to distinguish between the keys in the dataset. So in a sense, any key you take in the dataset corresponds to a unique path from the root to a leaf, and vice versa. Okay. So surf uses this truncated try and only looks at the truncated part to check for inclusion and see if any key is included inside of a given range. Okay. So this setup has several problems. The first problem is that of false positive rate robustness. So there are certain workloads where surf does not provide any guarantee whatsoever. And this one can see in this example that I've outlined right here. So if you have a query 0101 to 0111, this query corresponds to this small range that I've drawn here under the try. And if you look at it, you'll see that the left endpoint matches this path on the try right here. So the first 3 bits fully match the untruncated part of the try, but the last bit does not match the path, the part of the try that was truncated. So, but because this part was truncated, surf does not know whether the key that corresponded to this path is actually inside of the range or not. And because it wants to guarantee filter semantics, in other words, it wants to guarantee no false negatives, it has to always err on the side of caution and return a positive for this query, which in this particular case would result in a false positive. Similarly, if you have a different range like so, here the right endpoint matches the path, but it mismatches on the truncated part. So again, surf has to err on the side of caution and return a false positive. Okay. So these types of workloads where the query endpoints are very close to the actual keys, but the queries don't actually contain them, are known as correlated workloads. And these are very common in practice. The issue with surf is that it exhibits very high false positive rates, even close to 1 under such common workloads, which obviates the filter for many applications. Now, in principle, one can argue that you can truncate the try less in exchange for more memory to alleviate this problem, but this only delays the problem and does not fundamentally address it. We would ideally like a solution that addresses this issue fully under the same memory budget. Okay. Problem 2 is that of dynamic updates. So if you're trying to apply a range filter to a B-tree data structure or a database that supports OLTP or HTAP workloads, because these structures are subject to high throughput insertions, deletions, and updates, we have to be able to update our filters online at the same rate. But the issue with surf in particular is that the try is stored without pointers to optimize for space. So it's going to be very hard for us to efficiently add new branches to the try to support new insertions. The third problem is that of query cost. So because surf is a try, queries have to traverse this try, meaning that they have to incur a cache miss for every single level in the try, which is quite slow. Okay, so to recap, we have 3 key problems here. The problem of false positive rate robustness, dynamicity, and query speed. Ideally, we would like to have an optimal worst case false positive rate, regardless of the workload or its distribution. We would like to support dynamic inserts, deletes, and expansions. And we would like to have constant time cache misses for any query. So we want to have fast queries as well. At the time, no range filter achieved all of these goals at the same time. So that's why we came in and designed the Memento filter, which was the first one to simultaneously achieve all of these goals. So let's jump right in and see how the Memento filter works. So the Memento filter makes 2 assumptions. The first assumption is that it assumes that the universe of keys that it's working with is finite. This is a very common assumption in the sense that, well, it's basically going to imply that your keys are fixed length. And it's actually a valid assumption in practice because many applications operate on integers. The second assumption it makes is that range queries have a bounded length of big R, of a maximum range query length. This is also a common and fair assumption because long ranges are likely non-empty anyways. So if you have a long range query and you give the range query to a range filter, because the range query is non-empty anyways, the range filter is always going to return a positive. So in some sense, the range filter is only useful when you give it range queries that are empty. So we can safely disregard any ranges that are too long and only work with ones that have a length of at most big R. Okay. So with that out of the way, Memento filter takes the universe of keys, which in this case is this line right here, and the data set is represented as points on this line. And what the key idea it uses is it's going to partition this universe into some number of equal width partitions, like so. Each one of these partitions has a width of 2 to the log r. Again, r was the maximum range query length. So 2 to the log r is going to be the smallest power of 2 that is bigger than the maximum range query length. Now, if you do this, you can observe that queries will intersect at most 2 partitions at a time. This is because either a query is fully enclosed in a partition, or it crosses the boundary of 2 consecutive partitions. Okay. This allows you to localize the query, in a sense, to the partitions that contain it. So you can, just by looking at the offsets of the keys within the partition and comparing them to the endpoints of the query, you're able to answer the localized queries, which allows you to then answer the overall query. Now, what this means is for each one of the keys, you just have to store the offset of the key from the beginning of the partition, and that's going to allow you to do this comparison. All right, so that's the high-level idea. I'm now going to talk about storage layout, and then afterwards, I'm going to talk about how Memento filter implements its operations, insertions, deletions, queries, and finally, I'm going to touch upon the analysis of the filter. Okay, so the storage layout, it depends on how this partitioning scheme is done. So the way Memento filter does this partitioning is it takes each key and it looks at its binary representation. Then it splits this binary representation into a prefix and a short suffix, which we call a memento. The prefix is going to be the partition index that the key is a part of. So in this particular case, we have 5 partitions in our universe, 0 to 4. And the prefix is going to be, for key K, it's going to be 2. It's going to be the index of the partition that it's in. And the memento is simply going to be the offset of the key from the beginning of the partition. So recall again that the size of each partition was 2 to the log r, so the smallest power of 2 that is bigger than the maximum range query length. So the size of the memento simply has to be log r bits. Okay. Now the idea is we're going to encode all of the partitions in a compact hash table that uses linear probing. And for each partition, we're going to store a list of mementos that describes exactly what's going on inside of the partition. Okay, so what is this going to look like? Let's take our hash table right here. And let's say we want to encode this partition in the middle. Okay, so the thing that Memento filter does is it first gathers the offsets of these keys, which describes what's going on inside of the partition, in a list of mementos. So in this particular case, the first offset is 5, second is 7, and the third is 8. So we get this list. Then it hashes the partition index, so in this case, the value 2, to map the entire partition to a slot in the hash table. And it stores a fingerprint of that partition index, again, in that slot. Next to the fingerprint, it's going to store the list of mementos that it derived at the beginning. So we're going to have a structure like this. So in a sense, this structure is storing a fingerprint that allows you to match the partition, along with a list of mementos that describes what the partition looks like inside. This is what is known as a keepsake box and is the building block that Memento filter uses to support all of its operations. Now, because, well, partitions can have a varying number of keys inside of them, keepsake boxes can be variable length. So they have to have a variable length encoding in the sense that we want to be able to delimit them unambiguously. A simple solution to do so is to use a special character, in a sense, a special value for a slot, that's always put right after the last slot of the keepsake. Now, this is fine, but the issue is that this is very expensive in terms of memory. We're wasting a full slot for each one of the partitions, each one of the non-empty partitions in our universe. Instead, Memento filter minimizes the metadata overhead by employing a self-delimiting encoding for the keepsake boxes. This allows it to minimize the memory while still being able to process range queries at high speed. Okay, so before we get into that encoding, let's talk briefly about the slot structure of this hash table. Each slot is split into a fingerprint part and a memento part. The fingerprint part stores the fingerprint for the corresponding partition, and the memento part is generally used to store mementos. We'll see it in a second. Okay, so let's get into the encoding. Let's say we have the partition in our universe that has a single key inside of it. This partition is encoded simply by using a single slot, storing its fingerprint, storing the partition's fingerprint in the slot, and storing the memento of the key right next to the fingerprint. Simple. In the second case, we have two keys in our partition. So in this case, it's similar. We use two slots. We store a duplicate of the fingerprint, one in each slot, and we store the smaller memento in the left slot and the bigger memento in the right. If we have more keys in our keepsake in our partition, this presents an opportunity for optimization. So we're going to cut down on the encoding length and avoid storing duplicate fingerprints. The way this works is we're going to store the fingerprint only once in the first slot. We're going to store a 0 fingerprint in the next slot. So this 0 fingerprint is going to act as a queue or an escape sequence that tells the filter that this specific encoding of the keepsake box is in this special case. Then we're going to store the maximum memento next to the fingerprint and the minimum memento next to the 0 fingerprint. This allows us to have fast access to the maximum and minimum, which enables speeding up queries significantly. Finally, we store all of the other mementos in a sorted list in the slots that follow. So this is done by first storing a length parameter, which represents the length of the list, as a variable length counter. Because we want to support lists of any size, the counter has to be able to resize itself. And then we follow that up by storing a memento for each one of the other keys in sorted order in a misaligned fashion, so they don't have to line up with the slots. Okay, so that's how keepsake boxes work. Let's now talk about the operations. So let's consider inserts first. Here we have our hash table. All of these boxes inside of the hash table represent keepsake boxes. So given a new insertion, this blue key right here, the Memento filter simply hashes it and maps it to the corresponding keepsake box and simply inserts the memento into the keepsake box while maintaining the encoding. Deletes are similar. The memento filter simply hashes it, goes to the corresponding keepsake box, and removes the memento from the keepsake box. Queries are also similar. So given a query, we know that a query can only intersect two partitions. And the idea is we're going to find the keepsake boxes of the overlapping partitions and consider their mementos in answering the query. So in this example, we have these two partitions right here. The memento filter is going to hash these, and it's going to map them to these two blue keepsake boxes right here. And it's simply going to compare the mementos with the query endpoints to check for inclusion. Now, you might be wondering, where do false positives show up in this structure? This is because, well, mementos represent exactly what's going on inside of the keepsake box, so it's kind of counterintuitive where false positives show up. The reason for false positives is that we're storing a single fingerprint to describe the partition itself. So it might be the case that an empty partition might accidentally match a fingerprint that's stored for a non-empty partition. So when Memento filter looks at the mementos of that non-empty partition, it might accidentally return a false positive. So false positives occur due to having fingerprint collisions. They're not caused by the mementos themselves. Okay, so that's how operations are handled. Let's briefly talk about the analysis. We show in the paper that Memento filter achieves a false positive rate that looks something like this expression. So here F is the fingerprint length, and because false positives only occur due to fingerprint collisions, due to negative F is the collision probability that we care about. And because each range query only considers two partitions, we have to multiply this expression by 2 to account for the overhead of checking two partitions, each of which could err. Now this gives us the false positive rate. And one can show that this holds for any dataset and workload, which is the robustness guarantee that we desired. Range queries also are able to finish in at most 2 cache misses. This is because any range query checks at most 2 partitions, and each partition only incurs 1 cache miss because it's a single lookup in the hash table. Okay, so let's also talk about the evaluation real quick. So here I'm comparing the range filters in terms of false positive rate and their robustness. So on the x-axis, as you go from left to right, the workload becomes more correlated. So the more queries are going to be close to the keys, but none of the queries are ever going to contain any of the keys. So as you can, and on the y-axis, I'm showing the false positive rate of the queries. As you can see, Surf's false positive rate quickly jumps to 1, meaning that as the workload becomes slightly correlated. This is meaning that Surf does not provide any sort of filtering to filter out the range queries. Now, Graphite, on the other hand, which is another state-of-the-art range filter, is a static range filter that is robust to such correlations. So it has a flat, stable false positive rate, regardless of correlation. Now, if we add Memento filter to the picture, we'll see that Memento filter matches Graphite's false positive rate closely, while also providing you the benefit of supporting dynamic operations, so insertions, deletions, and expansions. As shown, it is also robust to correlate to any workload, so its false positive rate is a stable false positive rate across correlation degrees. Let's also take a look at the query time. So Surf has a fairly fast query speed, irrespective of the amount of correlation in the workload. In comparison, Graphite is much faster, but it also has a stable query time. And if we add Memento, we'll see that Memento filter is quite competitive and very close to the Graphite, while also allowing you to support dynamic operations. The paper compares Memento filter against all of the other baselines as well, so if you're interested in seeing that, please check it out. Let's also talk about the evaluation of integrating Memento filter with WiredTiger. WiredTiger is a key value store that is based on B-trees. And because Memento filter is the only range filter that is dynamic, it is the only one that can provide the benefits of range filtering to such a database system. So here we have this plot. On the x-axis, I'm showing you the fraction of non-empty queries that the database is subject to. So on the left, all of the range queries are empty. And on the right, all of the range queries are non-empty. And on the y-axis, we have query time. As shown, without a filter, the database has to access disk for all of the queries. So it incurs a high but stable query time. When we add Memento filter and trade off some of the memory in the database for Memento filter, we get an immense boost in query time, in query processing. As shown, on the boost in query time is proportional to the fraction of empty queries in the workload. So on the left-hand side, where almost all of the queries are empty, almost no time is spent on any of the queries. And it's smoothly interpolated between the two extremes. Now, this is nice, and it also does not come at a cost of insertions or ingestion capability. As shown, having Memento filter in the system and trading off some of the memory of the database for Memento filter does not adversely influence the performance of the database. In the paper, we also talk about CPU optimizations that we apply to Memento filter to improve its speed. We also explain how expansions and contractions are implemented. We do an extensive evaluation of Memento filter against all of the other baselines and various different scenarios. And we do a thorough theoretical analysis full with proofs. We also integrate Memento filter with rank and select quotient filters to illustrate how these ideas can be applied to other data structures. So in summary, we designed Memento filter, which was the first range filter to provide a robust false positive rate guarantee, a constant query time, and dynamic operations. However, due to the assumptions that we made, Memento filter did not support variable length keys and queries. To address this problem, we designed a follow-up called Diva, which is the first range filter to support variable length keys and queries, while supporting a semi-robust false positive rate guarantee and providing dynamic updates. It is also very fast, but it's slightly slower than Memento filter, with query complexities that are logarithmic in the length of the key. Diva is currently under review, so if you're interested in seeing how it works, please keep an eye out for it. Thank you.